Hello, this is the fourth part of the chapter 6.4, and we will talk about QR factorization of the matrices. And QR is just another way to break matrix into the product of two other matrices. For example, if we have A, which is m by n matrix of linearly independent columns, then our matrix A can be factored out in the product of two matrices, Q and R. Q is the matrix which column form an orthogonal basis for the column space of matrix R, A, and R is upper triangular invertible matrix with a positive entries on its diagonal. So again, one of them is triangular matrix, which is very convenient, and other one is contain an orthogonal basis space, so it's a very useful factorization. Let's try to factorize the matrix. For example, matrix A, 3 by 4 matrix, which look like that. Okay, so our column space is contain just 3 vector, x1, x2, x3, referring to the column of the matrix. So we can write them down explicitly, and if we want to write down matrix Q, we need to create an orthogonal or orthonormal basis. We already know the orthogonal basis if we are given the subspace spanned by the vector x1, x2, x3. We did it in the previous part of the series. And we find that it consists through 3 vectors, the v1, v2, v3, which looks like that. If you are confused about it, please go to the previous part of this chapter. Okay, but what we need is actually is orthonormal basis. So we need to have vectors v1, v2, and v3, which length is equal exactly 1. So we can go through normalization procedure. We calculate the length of each of this vector and divide vector v1 by its length, v2 by its length, and v3 by its length. Okay, let's calculate length of vector v1. Again, just use the square root formula, v2 and v3. So now we can form an orthonormal basis by taking each of the vector from orthogonal basis and divide it by its length. Okay, now when we have an orthonormal basis, we can finally form the matrix Q when we just write down our orthonormal basis vectors one by one, column by column. Okay. So now we have matrix Q, we have matrix A, we need to find the third matrix R. And we know that our matrix A is factorized by the matrix Q and R. So how we can write R? Okay, let's try to take this equation and left multiply it by the transposed matrix Q. We can do it, it's a matrix equation. And then there's a wonderful properties of our matrix Q. Then when it's multiplied by its transpose, it gives us an identity matrix. So the product of Q transpose by matrix A should be equal exactly the matrix R we are looking for. And we already have a matrix Q and A. So let's just write down our matrix R. So we take our matrix Q here and transpose it. So our first column, for example, 1/2, now became the row. Second column became second row, third column became third row. And we multiplied by the matrix A. And when we perform the calculation, we finally get our matrix R. And indeed, as theorem 12 promised us, it's a upper triangular matrix with a positive value on its diagonal. This is quite a tricky process, and sometimes it's quite labor intensive, so most of the time it's done using computer, but to fully understand it, it's very useful to actually do it several times by hand. So go now to the exercises for this chapter and conduct couple of QR factorizations.